We'll be back from the break. Still teacher Sulait with the simple harmonic motion. So I want to talk about the characteristics, x-tics of simple harmonic motion. Characteristics of a simple harmonic motion. So the characteristics are picked from the definition. Of simple harmonic motion. Hope everybody is still recalling the definition. We have said that this is an oscillatory motion whose acceleration is directly proportional to the displacement from a fixed point and is directed towards that fixed point. So that is the first characteristic. Acceleration being proportional to displacement. So acceleration is proportional. Have you seen how easy physics is? From the definition, we are getting the characteristics of this motion. And this is examinable. Whatever I write on the board, or whatever comes out of my mouth is examinable. Note it with a lot of care. If you are watching me as a recorded teacher, rewind your DVD. If you are watching me live, note whatever is coming out of me. And you can even record. You can try to recall my words. So, acceleration is proportional. To displacement. Displacement from fixed point or position, which we are calling the mean position. We are also going to discover today that the particle executing simple harmonic motion conserves energy. That the total energy of the particle executing this simple harmonic motion is being conserved. That is another characteristic. So total energy of the particle executing simple harmonic motion is conserved. And then lastly, we are going to see that it is an oscillatory and periodic. So, simple harmonic motion is periodic. Being an oscillatory, still it is again periodic. As we say that all oscillatory motions are periodic. Dear viewers, we'll be back from the break. It is teacher Sulait, still taking you through A-level physics of simple harmonic motion. So we had established the characteristics of a simple harmonic motion. Now it is high time we sample the types of simple harmonic motion. So types of simple harmonic motion. So this oscillatory motion, we are going to see that is of two types. And the first type I already mentioned it, and that is linear simple harmonic motion. And then number two is what we call the angular simple harmonic motion. So we are going to see how the period of oscillation varies in the different types of simple harmonic motion. However, people are not contented with the difference between oscillatory and then periodic motion. Now we say that simple harmonic motion among the characteristics is also periodic. And again we say that in the definition, the simple harmonic motion is an oscillatory motion. But remember, we also said that all oscillatory motions are periodic, but not all periodic motions are oscillatory. Now the question is, what is a periodic motion? A motion that repeats itself after an equal interval of time is what we call a periodic motion. A repetitive motion. Repetitive. It repeats itself after an equal interval. For example, when you swing a pendulum ball, you swing it, okay? That is a periodic motion. because there is a period of oscillation, and it will give a particular interval of time, or it repeats itself after a particular interval of time, the to and fro. Okay, so that is a periodic motion. Whereas an oscillatory motion, when we talk of an oscillatory motion, it is a to and fro motion about a mean position. So what can we see here? There is no mean position, or what we call equilibrium position, in a periodic motion. However, there is a mean position in what we call the oscillatory motion. For an oscillatory motion, there is a restoring force. Oh, there is a restoring force. So if a periodic motion has a restoring force, then at the same time it is oscillatory. But if it is only periodic without being oscillatory, then there will be no restoring force. Take a look at a pendulum, a simple pendulum. If we have a simple pendulum, this is the shape it can take. We can use a pendulum ball on a string. If I happen to displace my pendulum, for example, it was at position A, and then I displace it to position B. So a pendulum will swing, okay? It will swing in this direction, bypassing the position, and then finally comes to another new position. It is going to be displaced from the equilibrium position. So this is the displacement, and the displacement is going to be on either side. So since there is a mean position where it was resting, this is an oscillatory motion. And since now the motion repeats itself at an equal interval of time, then we shall say that this is also a periodic kind of motion. What I needed is talking about a restoring force. Once this particle reaches the far position, the maximum displacement, then there is a force, a restoring force, taking it back to the mean position. And then it bypasses it. When it bypasses it and reaches another maximum position, another restoring force is also seen, taking it back. So this is an oscillatory motion. Among the real-life applications of this oscillatory motion, which I did not give you, is the motion of electrons in a wire in an alternating current. If an AC current is towards a wire, is directed through a straight conductor like a wire, a very good conductor, then the motion of electrons. Remember, when electrons move in one direction, automatically current flows in the opposite direction. So the motion of electrons is going to describe an oscillatory kind of motion, which is simple harmonic, and there is always a restoring force towards the equilibrium position. So the distinct, or the difference between these kinds of motion, that is oscillatory and then periodic, we have seen a restoring force missing in what we call the only, a singularly periodic motion, which is not oscillatory. There will be no restoring force. When we look at oscillatory motion, we are seeing an equilibrium position. There is no equilibrium, and this is a stable equilibrium for an oscillatory motion. But if it is only a periodic motion, there is no equilibrium whatsoever, no stable equilibrium. So that's what I can also talk about. So maybe we can add that object will keep moving between 2 points if it is a circulatory motion. Yeah, but if it is only periodic, this may not happen. It can be periodic, but when an object is not moving between 2 points, 2 extreme points. We have an extreme point here and another extreme point. If I can call this one C, that can be an extreme point. But about a fixed position along any path, it can be along any path. And we have seen there is a restoring force. And this restoring force is directed towards the equilibrium position. So we have also seen that in an oscillatory motion, the restoring force or the net force on the particle or on the body describing this kind of motion is 0 at the mean position. And then we are also seeing that the mean position is the stable equilibrium, or is a stable equilibrium. So that's what we have seen. Very interesting. Now this takes us to something very, very interesting. Viewers, this interesting part is about the general considerations. What are we going to talk about in this concept? What are we supposed to note? First of all, you need to note that the acceleration is equal to negative omega squared x. Oh, very interesting. Depending on the displacement. If it is a vertical displacement, then we can talk of y, negative omega squared y. So general consideration. General considerations. I want people to get to know where now the equations of velocity, equations of displacement come from. Now, take a look at this. Assuming you have a body moving in a circular path, so circular motion is one kind of motion which is both oscillatory and then periodic. I want this to be a clear circle. How am I going to draw a clear circle, dear viewers? Help me. I want a clear circle. Okay, so that is a clear circle. Now, assuming this is the center of the circle. Okay. Now, let us have a fixed diameter on this circle. And this diameter, I'm calling it PQR. The center is Q. Very interesting. Now, assuming this is a horizontal fixed point also. Horizontal fixed point. And I'm also going to name it, for example, SO. This is O, point O. Now, assuming you have a particle moving with an angular frequency, with a particular velocity, and this particle is moving anti-clockwise, and it is at a point, assuming this point is B. Oh, very interesting. A particle is at point B at a time t. Very interesting. So its displacement from the fixed position is going to be the radius of this circle. And the maximum displacement, since this is the end point, is going to be A. That is maximum displacement, known as the amplitude. Very interesting. Now, if we try to see the horizontal displacement at any time t, the horizontal displacement is going to be x. From here up to there, that is x. If we look at the foot, okay, of this particle, the foot of the perpendicular still of this particle, vertically here, is going to give us, if this is a perpendicular, vertically, is going to give us the vertical displacement. So the vertical displacement is going to be what? Y. We can call it y on the vertical axis, vertically. We are trying to get the displacement. We want to express the displacement of this particle in terms of the angular frequency, the frequency with which the particle is moving. So a particle is moving with an angular frequency, omega. Omega is a Greek letter, and it is moving anti-clockwise. I want people to see what this happened. For a particle which started from here, moved up to a maximum displacement P. So it moved from this horizontal up to a maximum displacement. Now, assuming this is the position of maximum displacement upwards, and this is the position of maximum displacement downwards. So a particle moved up to when it attained the maximum displacement. This is what we are trying to do. It moved up to P. So you can see part of the wave. Now this particle comes back. Are you seeing this journey? It comes back to the equilibrium position. It comes up to this point. So which means from here, maximum displacement, back to the equilibrium position. Then it goes below the equilibrium position. up to around point R. Oh my dear, it comes up to point R. Then from there, it comes back to the equilibrium position. So from here, maximum displacement to equilibrium position. It goes back, since this is a repetitive, we have seen it is already periodic, it's going to be a repetitive kind of motion. Okay, a to and fro for oscillatory motion. It is a to and fro, to and fro. So we are going to continue with such a wave, and this is going to be a sine wave. We are going to consider such a wave in this kind of motion. So that's how it is going to be. So on infinite, it's going to be a kind of infinite motion. Oh, very interesting. So if we extract this triangle, look at this triangle here. The triangle I'm talking about is a right-angled triangle. And that is triangle, if this position is N, so that is triangle NBQ. Assuming the angle is theta at a point B, when a particle is at point B, it is displaced from the original position, from the equilibrium position, by an angle theta. Remember we said that omega is the rate of change of the angle with time. This angle is changing with time. So for us, we have timed this angle at a point B. So we get the value of the angle, we divide it. So we want to get a general consideration. What will be the vertical displacement? So the angle, if this angle is theta, automatically the angle is alternate to the angle up here at B. So at B, we shall have another theta. If this is 90, automatically this is 90 minus theta. But remember, this is the vertical displacement y, and this is horizontal displacement. Now, I'm more interested in both of them. I'm interested in both of them. So, if we consider the vertical displacement, we are going to see that the sine of theta, sine theta is equal to opposite over hypotenuse. But the hypotenuse is the amplitude or the radius of this circle. All other people can see that. So sine of theta is now going to be the opposite, which is y, over hypotenuse, which is a. So from here, we can go and say that this implies that my y is equivalent to a sine of theta. Very interesting. But if we make theta the subject of the formula here, theta will become omega t. Omega t. Can everybody pronounce this as omega t? So we are going to see that our y is now going to be a sine omega t. So the vertical displacement gives a sine wave. So we can keep this. This equation is going to change when time comes and we are talking about what we call the phase and the phase difference. What is phase? We are coming to that. And what is a phase difference? We are also going to come to that. But first note this. Now, also, if I talk about the horizontal displacement. So in the horizontal displacement, I'm going to see the cosine. When I talk in terms of cos, the cosine of theta, okay, from the Pythagorean identity of cos, equivalent to adjacent over hypotenuse. Cosine of theta is equal to x over a. So that is x over a. So from this, we can make the horizontal displacement the subject of the formula. So our x now is going to be a cos of theta. So therefore, we are going to substitute for theta, cos theta is omega t. And then we have x equivalent now to a cos omega t. That is very true. That is very, very true. Very, very true. But remember also, we said that acceleration is equal to negative omega squared of particular displacement. Assuming we are considering vertical displacement, it is going to be omega squared y. Oh, this is also a very important expression to note. We are talking about general considerations. General considerations. So all these should be considered in a general outlook of this simple harmonic motion. However, by definition, acceleration is change in velocity over time taken. So acceleration, we know very well that acceleration is equal to change in velocity over time taken, change in time. And velocity is equal to the change in the displacement over time taken. So dy dt is our velocity. However, we have y, which means we can apply some trigonometric calculus. Yes, we can go and differentiate. Do you know what we call differentiation of trigonometric identities? That is the question. Now, in this kind of arrangement, we can go and say that this implies that velocity is equal to d dt, but y is given somewhere. We have already talked about y, and y is a sine omega t, a sine omega t. So when we differentiate a sine, we know very well that we get a cos. Oh, very interesting. When we differentiate a sine, we get a cos. However, if we are differentiating such a compound angle, okay, or such an angle, we first differentiate the angle. So when we differentiate omega t with respect to t, we get an omega. So omega comes in from. So what we shall get here will be omega a, okay, then cosine of, that is the differential of the trigonometric identity, cos omega t. If this is going to be difficult for you, then which means you have to keep theta. Go and keep theta. You will keep theta. But still it will not give you exactly what I have here, the omega t. Because when you differentiate, a t will not come in. We need to differentiate with respect to t. So there is no way you can keep theta. So this is very true. The velocity is equal to omega a, omega amplitude cos omega t. So can you first remove this? Then we come and give an equation for velocity in terms of displacement y, in terms of omega, the angular frequency omega, and then the amplitude without a trigonometric identity. First remove that. After clearing some space, we want to continue from this expression of velocity, but we need to get the real expression which is used in form of a given angle or ungiven angle. If they have not given you the angle, okay, which expression can you use? Assuming theta is not there, which will give us now the omega t. Which expression are you going to use? Can we get a general expression? However, you should be noting all these. These are all general considerations. We shall need them with the time. Okay, very easy topic, a very simple topic. Now, from where we stop it, we had already established that V is equal to omega A, where A is the amplitude, and then cos omega t. Remember when you are told maybe to prove the expression for V, as we are going to prove it, you need to back it with words. You need to take a consideration. You remember my words. I took a consideration. I considered a particle which was describing a circular motion, moving with an angular frequency, omega. Then I considered some fixed diameter and then a fixed horizontal position. Then I considered a particle at a time t when it was at a point b, if you can rewind my words, at a point b. Then its displacement from the fixed position, we saw it as r, the radius, which is equivalent to amplitude, because maximum displacement from rest position or from equilibrium position is amplitude. Then from there we saw the rate of change of the angle, that at the time t, the angle has changed by theta. We considered theta. You need to tell the examiner. This is not mathematics, where we need only numerical values. You need to talk to the examiner. So any proof, any derivation, you need to use words like consider. Then talk about what you are going to present. If there is a diagram, explain it. Talk about it, my dear. So that is the physics way of now dealing with some proofs and then numerical work. Now, from where we have stopped, we can tell the examiner that, Mr. Examiner, sir, using the Pythagorean identities, that from a Pythagorean identity of sine squared of a given angle, assuming the angle is theta, then plus sine squared, that is cos squared now. Oh, so sine squared theta plus the cos squared of theta, we know very well that it is equivalent to what? It is equivalent to 1. If it is equivalent to 1, we can make this cos the subject of the formula. Now, assuming it was cos omega t, because theta is omega t, so which means we shall have sine squared of omega t, then plus cos squared. But let us leave it in terms of theta. We shall substitute. So from here we can make cos theta the subject of the formula. So the cosine of theta is going to be the square root of 1 minus the sine squared of theta. So my physics students, always note this. If I tell you sine squared of theta, this is the same as sine theta squared. The square doesn't come onto the angle, but it goes onto the trigonometric ratio. So the ratio is the sine, the trigonometric ratio. That's where it goes. That's why we put it here. Okay, so if that one is God, then we can substitute. We know the value of sine theta. We obtained it as y over a, where a is the amplitude and y is the vertical displacement. So we can go and say that cos theta, Mr. Examiner, sir, is now going to be equivalent to the square root of 1 minus sine theta is y over a, so that is y over a squared. We are squaring the trigonometric identity. So, which means that cos theta now is going to become, if we get the LCM, okay, and you can try to get the LCM. So, we can get just a common denominator, such that now we have 1 square root of a squared minus y squared all over a. So that is the value of cosine of theta. So we can come and substitute it here to get an interesting expression. People are asking, where have I got this? Oh my dear, people are slow. I've seen somebody's email running on my screen. Okay, a person who is asking this is what we have done. We have dealt with what is inside. First square this. If you square, you have, remember everything is under square root. So under square root, we have 1 minus y squared over a squared. So we went and got the LCM, but still under square root. So the LCM, remember this is a squared, is a squared. So a squared divided by 1, we get a squared, times 1, that is a squared, minus a squared divided by a squared, that is 1. 1 times y squared, that is y squared. Everything under square root. So we have now distributed the square root. We have redistributed the square root to the numerator and the denominator. So we are going to see that once the square root goes onto the denominator, it cancels out with the square. That's why we are no longer having a inside the root sign, but only the numerator, a squared minus y squared, is the one inside the root sign. So you accept to first remove this work. However, you note it somewhere. We said we are going to supplement on this displacement with a phase and phase angle. We are also a phase difference. We are also going to supplement this and then get a new expression for the horizontal displacement of any particle given any path, but towards the mean position or the equilibrium position. So dear viewers, hope you have now got where that one comes from. So we can come here, remove this. Oh, are you still recording our expression for velocity? You can rewind and then see it. So we can substitute. So from velocity, which is equal to omega A cos omega t. So the cosine of theta is now the same as cos omega t. So where there is omega t, we can just put this. So which is the same as cos omega t. Because theta is omega t. We saw it from the definition of angular frequency. So from here, our velocity now is going to become omega A times this, which is the square root now, okay? The square root of a squared minus y squared over a. That's what we have. Very interesting. Very, very interesting. So in this kind of arrangement, you will see that the AA will cancel. So the expression for velocity is going to become omega square root of a squared minus y squared. So this is general. It can work on the horizontal displacement if the displacement was x. So we will have x here. So this is a very general formula, for velocity small v. When we try to square both sides, we can get another interesting formula. So a v squared will now become omega squared into a squared minus y squared. This is a very interesting formula without a square root, which we normally use to calculate velocity. However, now this velocity, we are going to give it a plus or minus. There's where velocity is positive. That is because a particle is oscillating between two fixed points. Remember what I gave you? I gave you z and then z prime. It is oscillating between those, passing via the mean position, the equilibrium position, where now the net force is 0, and the acceleration is also 0. So this is very, very interesting. You have to note it somewhere. So immediately after a break, after you memorizing all this and how to come up with this proof, I'm coming back with something very interesting. Don't go away, stay tuned.